Thanks. Okay, thank you for the invite. I'm sorry I couldn't be there in person. I should also mention that I actually have never been to RSS, so I'm sort of a stranger to this community, so I'm going to be talking about planning with LLMs and LRMs with some specific focus on robot planning in particular, and I sort of share with you what works and what doesn't work from based on the research that we have done. So it's a bit of it's kind of something is now for something completely different based on the various talks that I've heard this morning. Essentially, most of the talks have focused a lot more on the trajectory planning for robots, which is extremely important, but have always ended saying in future we'll also start thinking about long range, long horizon planning. In fact, my talk is all about long horizon planning. Actually, I come from automated planning community where we from the robotics perspective, you can think of us as the task planning people, which would then be connected to trajectory and motion planning stuff. So this is actually a part of the whole, but then, if you have long horizon planning, you do care about task planning. So from that perspective, we've been looking at what can LLMs and LRMs do, and we've done a bunch of work on that. And actually, this is a very short talk. I mean, as I found out, it's like a 20-minute talk, obviously. So I actually am showing you a 3-hour summer school lectures that I just gave last week in Italy. That is available in case if you find this very fast take on the summary of this work interesting to you. Okay, so getting to LLMs and LRMs, large reasoning models and large language models. I will talk about VLMs, which we talk a lot about a little later. So it's obviously upfront, there is no real reason to believe that large language models, standard large language models, will actually be able to do long horizon planning because they are sort of large scale system one for the humanity at large, and planning and deliberative reasoning is typically connected to system two. And yet, of course, obviously this entire workshop as well as a whole bunch of work before has found that, in fact, foundation models or large language models and large reasoning models can be useful in planning tasks. And so one tricky part, I just sort of show this dense slide to point out that planning is typically needed exactly when the world is non-ergodic from the agent's perspective. That means the agent can get into a state from which it can't come out, and that's very important. That's why you need to actually do pre-planning beforehand. And the robustness of the plan, of course, is how often it actually winds up achieving goals. And then finally, the last part is quality of the plan. From task planning perspective has always been a bit of an amorphous thing. In addition to just reaching the goal, there are ways of actually reaching the goal in the trajectory planning and so on, which would be aesthetic and, be seen as reasonable by humans versus not aesthetic. And in fact, we'll see that actually LLMs are amazingly good for capturing some of these quality constraints, but not actually very good at ensuring correctness. So that sort of comes back to this aspect that I keep mentioning, that LLMs and generative AI in general capture the distribution of the data they're trained on, and style is a distributional property. And so LLMs are actually able to learn this. And when I say LLMs, of course, VLMs too can learn this. And they have been actually called vibe machines, as you know. In fact, I would say that for slightly like a partial outsider for your community, I would say that a big part of the success of foundation models in robotics has really been the ability to learn style from demos to do trajectory planning. That's much of the success, and it's actually a very hard problem before, and LLMs have sort of made it more possible. Correctness and factuality is actually an instance level property, and LLMs don't particularly guarantee this. Civilizationally, we have had always thought that style is harder than content, and so that's part of the reason why when you see LLMs doing style well, we assume that they might do correctness and content well, that they actually don't. Another interesting part about this is people tend to confuse the computational complexity notions with the way LLMs guess solutions to prompts. It's worthwhile remembering that whether the prompt that you give to the LLM is corresponding to a constant complexity, constant time, or quadratic, or NP-complete, or semi-decidable problems, especially for standard LLMs, the moment you hit return, it starts actually giving out tokens. So it's not like it is actually thinking and searching for the solution for the problem and so on. And so computational complexity intuitions tend to lead you astray. One of the ways they actually have led you astray is typically in the cases where you think that maybe they're not good at generating plans, but they can verify them because verification is cheaper. But it turns out that they're actually bad at self-verification too. We'll see that in a minute. But on the other hand, they're amazingly good at background knowledge capture. And so that basically they can capture common sense, domain knowledge, even things like theory of mind and analogies, not perfectly, but better than pretty much anything that came up before them. And so they're actually very useful from that perspective. And as you know by now that state of the art in LLMs, of course, there's the standard LLMs, and then the reasoning models, which basically add to the standard LLMs two important ideas: test time scaling and post-training. And what I basically want to say is this is a sort of a foreshadowed summary, because I really have no idea whether I'll get to the whole talk, but that in fact standard LLMs trained on the web corpora we actually have shown in our work that they are known to have severe limitations on the planning and reasoning tasks, especially long horizon planning and reasoning tasks. And they could, however, be very good arbiters of style. In fact, the first stuff was actually shown in like NeurIPS 2023. There are several papers there. And the second one about the style is in COMB last year. And that sort of shows how LLMs actually can take trajectories, all of which reach the goal, but then can critique them in terms of whether they are pleasing from a human perspective and the unsaid constraints perspective. For example, if you ask for a pair of scissors, making sure that the scissors are not given with the pointy end towards the human is something that's an unsaid constraints. And actually, LLMs are pretty good at capturing those sorts of things, and VLMs in this case. They could, however, LLMs can still be used as generators in a generate test cycle, even for long horizon planning tasks, and then have external verifiers that actually, not LLMs themselves, but external verifiers that actually check if, in fact, these the plans that they guess are actually correct or not. And this is sort of an LLM modulo framework that we have talked about in our work, but it's also been seen as test time scaling ideas in other part of the world, other parts of the LLM community. And that actually does tell you how to use LLMs to give correct plans, because you can actually generate and then test to make sure that they're actually correct. The improved reasoning abilities can, of course, be compiled back into the base generator. That is pretty much what has been called post-training. And the post-training approaches actually is sort of, you can think of post-training as doing test time scaling, except during a training time, where you actually generate a large number of synthetic data problems, and then you're essentially checking whether the LLM is able to guess the correct solutions. And for the ones that lead to the correct solutions, you actually improve you push the parameters using RL towards those trajectories. And so one other thing, of course, is that these kinds of post-trained LLMs have been called LRMs, and those do better in long horizon planning tasks, but they still do it only in this incremental way. You train them to actually get better at, let's say, 4-block stacking problems, and then you have to retrain them to get better at 10-block stacking problems, and then you have to retrain them to get better at 100-block stacking problems. They're not learning algorithms, they're learning to actually go farther in the inference horizon. And there's a bunch of issues about anthropomorphization of intermediate tokens in the LRMs as reasoning traces that are quite questionable, and we talk about that in our work. And this is a useful thing for some of you probably to know, that to kind of look at that. In general, when you're thinking about in versus out of distribution, especially for planning and long horizon planning problems, you really are thinking about deductive closure. So if I can show a robot how to stack 3 blocks, can it stack 10 blocks? Can it stack 100 blocks? And from a human perspective, yes, of course you can do that. But from a LLM perspective, unfortunately, that winds up not being possible. And part of what happens essentially in the way we have got LLMs to do better in out of distribution, as this Nathan Bainak cartoon shows, that if your model can't do well out of distribution, just get the out of distribution back into the training so that it will be in distribution, and so you do well. And this actually worked pretty well, except for reasoning problems. just getting the entire reasoning problem instances back into the training distribution is impossible because you have to get 10 blocks, 20 blocks, 30 blocks, etc. And because it's not learning the algorithm. And so that winds up actually being a problem as to why LRMs, despite doing well at certain lengths of planning problems, still fail as the length of the planning problem increases. So again, going back to standard LLMs, they actually can't plan. We have shown that in Unit 23, especially when there are interactions over the long-term or long horizon planning. And sometimes they can actually memorize the plans and then regurgitate them. And there's the test time, the whole training test data contamination is like a feature rather than a bug these days in LLMs. And so one of the things you have to do to check that they're actually not remembering things is to actually make sure that they haven't seen the problem that you're asking. And we basically did this mystery blocks world where you actually change the names such that it won't look like blocks world. And we have actually shown that most standard LLMs do pretty badly on mystery blocks world. It's the same exact blocks world environment. It will be doing, the classical planners will do just as well on this as well as the previous blocks world. But obviously, LLMs die on this. It turns out, again, chain of thought, React, and fine-tuning, they're actually very close to your heart in the robotics community. They do well for short horizon, more trajectory level planning, but we have basically shown that they don't do well that much. They don't generalize enough for long horizon planning. In particular, if you you give a chain of thought prompt to actually do well, even for something as simple as blast data concatenation, how to do it on like a 2-3 word problem, it doesn't generalize to 18, 20 word problem. And it also doesn't generalize to longer planning blocks word problems. This should not be surprising because just giving advice and expecting LLM to take the advice would have been AI complete, because that's what actually McCarthy said original goal of AI is supposed to be. On the other hand, of course, lots and lots of people basically assumed that they are indeed doing planning, even standard LLM's case. And part of the reason is there tends to be a confusion between planning knowledge and plan generation for long horizon. LLMs are very good at planning knowledge, but they're very bad at plan generation, especially when there are interactions. And we can show that by taking something like blocks world, removing all the interactions between the actions such that actions can basically be, the sub-plans for sub-goals can be concatenated in any which way, and the plans can actually work. And in those cases, you find that LLMs actually do better. There's higher, longer green, more green area. But when there are actual interactions, they do much worse. So you can actually argue that LLMs can plan if you're talking about short horizon, but you can also argue that they can't plan if you're looking at the long horizon. They're actually very good at knowledge capture. And in fact, in NeurIPS, another NeurIPS paper, we talk about how you can use them to actually acquire domain models. And that's a very useful thing because that's a very manual thing normally in traditional planning domains. So that there we go from like standard LLMs to which actually are doing very well on the sort of system 1 style stuff to system 2 or system 1+2 LRMs. What can we do about it? One idea is test time scaling, where we actually just use LLMs to guess plans and have a verifier check. And my favorite way of doing that is what we have called LLM modulo, where you have LLM in the middle generating guesses and a bank of verifiers of different kinds, checking to see whether they're happy with the solution, the guess, and if not, providing a back prompting. Instead of backtracking, you now have a back prompting to actually come up with a better solution, asking LLM to come up with a different solution. And this basically, this loop ends when in fact the majority or all critics are actually happy. So in this case, the bank of critics wind up giving different kinds of basically the guarantees that the plan that is coming out is actually satisfying the critics' constraints. And notice that we didn't talk about planners, but we're talking about verifiers. It turns out that verifier, if you have a verifier, you can invert it to get a search algorithm, a planner. But it turns out that verifiers are composable, and so they can actually be bundled together. You have a verifier for timeline constraints, you have a verifier for causal proof constraints. And interestingly, you can even have a verifier for style of the trajectory. And then basically for the correctness, if the verifiers are actually sound and complete, then LLM modulo would in fact only send out plans that will be correct. In terms of the different types of critiques, the style critiques are the only ones LLMs themselves can do. Correctness ones have to be done with external critiques. If you try to do self-critiquing with LLMs on the long horizon planning, there's an ICLA 2025 paper that basically shows that their performance worsens if LLMs actually check whether their guess is correct or not themselves, and they try to get into a loop, they might actually walk over the correct guess and end up in the wrong guess because their verification is no better than their plan generation. And this is one of the things that people assume they should be able to do better just because verification has lower complexity, but that doesn't work for LLMs necessarily. On the other hand, they're actually very good for style critiquing. This is a Comb paper. This is the only one that you have with the actual robot moving lots of stuff, where basically we showed that, in fact, if all of these trajectories, all the plans, for achieving the goal are correct, but the trajectories are differing, it can actually critique the trajectory in terms of, okay, for example, don't give the pair of scissors with the pointy end towards the human, for example, that sort of a thing. It turns out that you can also use LLMs as style critics for human preference proxies. That's an HRI paper. I don't have too much time to go into it, but that'll be a useful thing to remember. In general, LLM modular improves performance, including with guarantees. That's a useful thing. And you can actually argue that things like alpha geometry, alpha proof, Fluent search, they're all essentially using LLM modulo style ideas. Even program synthesis community winds up using verifiers, where the verifier essentially is a bunch of sort of the unit test and the code guess is actually being given to the Python interpreter along with the unit test, and that winds up being a partial interpreter, partial verifier. So that's the test time scaling. The last part that I just want to say is, if you know how to improve your performance, of a generate test framework, Minsky over here is one of the founding fathers of AI, basically said intelligence is integrating test part of the generate test into the generate part. And that's pretty much what actually post-training can be seen as. Even in the context of something like LLM modulo, if you have solved a problem, you can remember the solution and the original problem and then fine-tune the LLM over a period of time, and then that can improve the performance. And of course, there are better ideas that have been tried. One particular one is just actually train with problem and intermediate tokens and the solution using either SFT or RL post-training, and that seems to improve performance more significantly. And so, in fact, when O1 came along in September last year, Noam Brown basically said that, look, basically block-solved planning can be solved well by O1. So we actually took him at his word, and we looked at evaluated more carefully what they can do. That's actually been published in TMLR. And what basically it shows is, yes, in fact, it improves performance for the short horizon at a certain level of horizon. But as the length of the plans increases, LLMs will again continue dying. And then so it's both a very big positive that actually you are able to push the inference horizon over which you have good correctness with this LRM style reasoning, but it also tells you the essential problem of trying to do planning just by kind of slowly, incrementally compiling the verifier signal into the generator. That tends to be a very costly way of doing it, and it tends to be also inefficient. By the way, some of you might have heard the whole brouhaha of the Apple paper last week. It turns out I don't know whether they knew this or not, but basically they more or less repeated everything that we have done other than Tower of Hanoi problems. And then it just turned out that actually got this particular limitation of LRMs much more into the public thing. So we did get New York Times to say that we did this before Apple. DeepSeek R1 actually is also reasonably competitive with O1. And then one last thing I want to say before we end is that I showed you this LLM modulo. I tend to think of these large reasoning models, especially for the long horizon planning, as better generators. They are still not guaranteed correct, but they are better generators. And so instead of LLM, I can put an LRM in this LLM modulo framework, and that can improve the performance of O1 and O style approaches furthermore with guarantees. We have shown that in that TMLR paper. And then there are a bunch of other things that are actually kind of in the 3 lectures that I put out there about the post-training approaches. In particular, essentially, you can think of all what's going on in the post-training and distillation as incrementally compiling the verifier signal into the base model, and rather than learning the algorithm in one fell swoop. And that winds up having its own inefficiencies, and you should be aware of them. And it's partly because of the way this actually shows you why the way LLMs and transformers learn reasoning problems is this very incremental way. Multiplication is only becoming better slowly rather than just learning the multiplication algorithm. So there is a paper which sort of argues, a very recent paper that we wrote, that we show that intermediate tokens of the large reasoning models cannot really be expected to have many semantics, and that some of the things about RL doing reasoning because it increases the length of the intermediate tokens are also equally questionable, because it turns out that the way the MDP is set up winds up pushing RL to actually look for longer traces when the problem is likely to fail. So in summary, again, standard LLMs have problems that basically they're more like system 1. They can, however, be used as generators, and in the generate test cycle, again, these are mostly about the long horizon planning. For short horizon, basically, you don't have to worry about interaction. And then the reasoning abilities can be compiled into LLM with either SFT or RL fine tuning. The resulting LRMs can still have no correctness guarantees, but are better generators. And the anthropomorphization of intermediate tokens as reasoning traces is questionable. We actually have a position paper on that too. And if you're interested, there's a lot more about this in these 3 lectures that you can look at. And then these 2 papers that give you a very quick overview of what I just discussed. And I will stop here. And then if there's any time for questions, I'll take. Thank you for your attention.
Thanks for a great talk. Any questions? Okay. Yeah.
You very briefly touched on LLMs or LRMs that output code and things like that as being essentially a subset of the LRM modulo concept. Can you expand on that and how that interacts with the ability to do verifying and analysis of the output and things like that?
Sure. So in fact, this is pretty much non-controversial in the few people that actually do verifiable code generation with LLMs. So what we are saying is LLMs and even LRMs are very good at generating code that's almost correct. And with a human in the loop, they have become extremely useful tools. That's why your cursor and all these things have become amazingly popular. But if you actually want to give some kind of a guarantee that the code that you have is not human verified, but it's automatically verified, then you still have to have the code that is generated being subjected to verification. And the usual verification would be with respect to, let's say, a bunch of unit tests. And the nice thing is that Python interpreter, along with the unit tests, become an external verifier for anything that is in Python syntax. And so it winds up basically being able to tell whether or not it's passed all the unit tests, in which case, at least, if it failed any unit test, you know that for sure that there's a problem with the code. If it passed all the unit tests, then we still have unmodeled errors that haven't been modeled by the unit test, but at least it's better guarantee than otherwise. So that's sort of what we mean by this test time and the verification being done to make sure that the code is actually correct. In the cursor style thing, you, the human, are the verifier. You are looking at it. And in fact, actually, there's an interesting way of looking at, if you're talking about automated, then we're talking about Python and unit tests. If you're talking about humans, then you have to just make the code that is generated easy enough for people to grok, so that somehow they can spot any issues with it before they put their job online with that code. And both are being done right now. I think the cursor thing basically shows that the guess is pretty good, but there's no guarantees. And then if you want automated guarantees, then you need to do this verification cycle. And that's the LLM modulo is what I